Hey guys, and welcome back. Today we're going to be solving LeetCode number 136, single number. The question states that given a non-empty array of integers nums, every element appears twice except for one. And we're supposed to find that single element. So our solution must have a linear runtime complexity and only use constant extra space. To gain some intuition for the problem, let's think about the first example. Essentially what we have is an array 2, 2, 1. Basically, we know that there's two 2's in the array and that there's 1, 1. So in this case, of course, we would like to just return 1 since it's the element which has frequency of 1. Okay, now that leads us to our first approach, using a hash map. Essentially, what we would like to do is iterate through the entire array, keeping track of how many times each item appears. So we can call this hash map frequency. And essentially, using the second example, we would iterate through this array, adding to the hash map each time. So on the first iteration, we add a new element, which is 4 with frequency 1. On the second iteration, we would add the second element to the dictionary with frequency 1. And then the third with frequency 1, and then update the frequency of 1 in the hash map. Instead we would make it 2, and then same thing with 2. Okay, and after we've traversed the array, we know that we're done adding to the hash map. Then at this point, all we have to do is iterate through each of the elements in the array, looking for the one with frequency 1 and returning the associated key. So that's the method of using a hash map. And this actually takes O of n times, since we pass through the array once and we pass through the hash map, which takes up to n steps at most. Now the space complexity of this algorithm would be O of n as well, since the hash map can take at most n space. Let's consider another method which can actually reduce the space complexity but up the runtime, which is sorting. Essentially, we're going to use example 2 to illustrate the point. So the nums array is equal to 4, 1, 2, 1, 2, and then after a sort, 1, 1, 2, 2, 4. What's important to note here is that each time a certain element appears in the array, if there is another element in the array with the same value, it will be adjacent to it. And it's also important to note that in the question description, it says that every element appears twice except for 1. So that means, given this index of the array, the next element must be right beside it, if there is exactly 2 of this element. However, in the case, say, where we reach the end of the list, or maybe there's another element in the list, when we check for whether or not there's another 4 adjacent to this one, we'll encounter a different value instead of 4. And once we reach the end of the list, we'll know because we haven't early returned at that point, because whenever we find the value that occurs only once, we'll early return. But if we haven't at this point, then we know that this is the value that must be returned. Okay, so then how exactly are we going to go about this? Essentially, what we're going to do is we're going to begin at the first index, check the value at the one adjacent to it. If it matches the one at the first index, we'll move on to the third index, checking whether the value adjacent to it matches that index, and so on and so forth. This is all great, but there's actually a quicker solution that is not O of n log n, of course, because of the sort here, but has the same space complexity, O of 1. Now for the third method, bit manipulation. To gain some intuition, what we're going to do is list any number of binary strings that is greater than 2, so that all digits of equal significance line up. So essentially, let's think of some example.
1 0 0 1 1 0 1 0 0 0 0 1 1 0 0, and then again 1 0 0 1 1, and then 0 1 0 0 0.
Now you could imagine that each of these binary strings is associated with some integer value. What I did over here was that I wrote every element in this sort of list of binary strings. I wrote some of them twice. Now the reason for that is to illustrate how we can actually leverage the binary representation of these numbers to get us the solution. The key here is using the XOR operation. Okay, essentially what is important to note is that with XOR, what we do is we consider one column of the binary string at a time. So let's consider the first column, 1 0 0 1 0. What I claim is that each column will return 0 if there are an even amount of 1s, and 1 if there are an odd number of 1s. Alright, now how am I going to prove my claim? So what I'm going to say is that XOR is associative, which is a property of XOR, essentially, which means that no matter how we place brackets around and evaluate the, I should put little symbols here, no matter how we evaluate XOR, we're going to get the same result. So in this string, for example, what I do is first I'd evaluate all substrings with zeros. Okay, so in this case I'd evaluate this first. Alright, well 0 XOR 0 is just 0, and then XOR 1 XOR 0, and then we get to this point, but if I place brackets here, 0 XOR 1 is just 1, and 1 XOR 0 here is again 1. So what we realize is the number of zeros actually didn't matter in this case. Only the number of 1s matters. Another important thing to note is that the array will always be of odd size, because for any element that doesn't have frequency 1, there's exactly 2 of them. In the case of the element that appears only once, the first column will have exactly an odd number of zeros, which means an even number of 1s. So odd zeros, and that one implies an even number of 1s. Okay, well, what does this mean? Well, an even number of 1s is the same thing as producing 0 when that XOR operation occurs. And the reason for this is, let's just say I have some number of 1s. Now, I'm just going to put boxes around them to note, or to make it more clear. Now, consider the XOR operation between all of these 1s, right? Alright. Now, when we perform the XOR operation, and again, since XOR is associative, we can consider each of these pairs like so. Now, for each pair of 1s, what they evaluate to is 0, 0, 0. Now, 0 XOR 0, this just produces 0. Now, if we had an even number of 1s, we would just get 0 over here. But if we perform the XOR operation with an odd number of 1s, now we have 0 XOR 1, which is equal to 1. So now we know that an odd number of zeros produces 0 in one of these columns, and then an odd ones produces a 1 in a column, which means, and it's important to note that for the number that we would like to output, there will be an odd number of zeros or an odd number of ones in a column, because each occurrence of a number with frequency 2 just makes the number of zeros or number of ones in a column even. And then this single frequency element just offsets that number, which means that if we take the XOR of each element in the array, what we'll end up with actually is exactly the number that occurs once. The running time of this algorithm is O of n, since we essentially just need to loop through the array of elements and perform the XOR operation. The XOR operation takes constant time, and since we only create one new variable, which will be just some accumulator, we've only used constant extra space. Alright, so for the written solution, it's very short and simple. All we need to do is set up an accumulator, which I'll initialize as 0, because 0 XOR some value actually just produces that same value. We want to iterate through each of the elements in the nums list. So for nums in nums, we want to say accumulator XOR equals num. And then from here, all we want to do is return the accumulator. And that's actually all the code that's required of us. And then we can submit the solution. And that's it. Thank you guys for watching, and I will catch you in the next one.